Tyler's with us. And I think we're on Thermo Thursday, October 22nd. Let's see who we've got here. We've got Alex, Nathan, Nicholas, Taylor, Julian, Mohammed, Bryce, Tyler. I got a good crew here. Okay. Welcome to Thursday morning Thermo. The topic is the Carnot cycle. I could write that down. The topic is the Carnot cycle. Did you have any comments or questions for me before we begin? Nope. Taylor says nope. How about anybody? Bryce says nope. Okay. Well, all right. Now, what you have for homework, I think it's 549. Let me look and see, make sure here. This is the 22nd. Yeah, you've got 549. But you also have 533. Maybe we should do that 533. Well, let's see what that is. I graded some of your papers here a while ago. And I want you guys to, I want you to draw these schematics the way I like them. It's not the way the book does it. But this is part of your homework. And we could just do it together. It's a heat pump. Now you make your cycle, and you do it counterclockwise. And you put your coal down here. This is the low temperature. And this is going to be the high temperature. And you have to input energy. Now they're using, let me read this. The house is to be maintained at 20 degrees at all times. Well, that's this one. See, this is 20 degrees Celsius, which is 293 Kelvin. And outside it's -10. It's a cold day in Oklahoma. Well, that's 263 Kelvin, isn't it? The rate at which heat is lost from the house is estimated to be 25 kilowatts. See, your house is radiating heat out. It's got bad insulation. And there's 25 kilowatts that you're losing. And so what you have to have is you have to have a QH dot equal to 25 kilowatts to replace those 25 kilowatts that you're radiating out. Now this is QL dot, and this is your power. What is the minimum electric power required to drive the heat pump? Okay. Now, the book does a different way of drawing the schematic. I want you to draw this schematic the way I'm teaching you to do it. Just humor me, okay? You'll be through with me soon in what, December? And you won't have to listen to me anymore. And you'll go on to OSU or wherever you're going, and you can do it the way they want you to do it. But right now, I want you to draw your diagrams like this. Now, a heat pump has a counterclockwise PV diagram for its cycle. See, this is a cycle, and I want you to put the hot temperature here, the cold one down here, and here's your heat transfer to your refrigerant, and this is your heat transfer from the refrigerant to, in this case, to your house. Now we have a beta prime is what they have. We have an actual and we have a maximum. Now these things are called coefficients of performance. Now the actual one, what it is it's this QH dot all over W dot, which you could write as QH dot minus QL dot. In this case here, this will be 25 kilowatts divided by 25 kilowatts minus your heat transfer rate at the lower temperature. We don't know what it is yet. But now we have an equation based on your Kelvin temperatures that will give you the maximum possible coefficient of performance of your heat pump. But see, we know all of those. The TH is a 293.15 K, and this one is 35. Do I need to explain how come going from minus 10 to plus 20, it's not 35. Let's try 30. Yeah, there we go. From minus 10 to 20, that's a change in temperature of 30. Yeah. And so this is equal to, let me do that, 293.15 divided by 30. Now, if I goof up, you guys jump on me now. Let's make sure we get this right. I'm getting 9.77, I don't know, 1, rounded off to 2. You'll discover these coefficients of performance are always bigger than 1. Efficiencies are always less than 1, but these betas are always bigger than 1. Now here's how we're going to solve this. We're going to set these equal, and that way we can get our minimum power. So set them equal, here we go, 25 over 25 minus the QL dot equals 9.772. Okay, now I'm going to shut up for, well, guys, this is I'm doing your homework for you, you lucky people. Let me get some scrap paper. I think I can do this. Just a minute. Got to get some scrap paper and do this. And I want you to do it too, and we'll see if we get the same answer. Here we go. Well, I got an answer. I got this here is 22.44 kilowatts, but I'm going to wait till I hear a couple of uh-huhs.
Yep.
Uh-huh.
There, well, we're doing good. And now, see, we can get this power input. Because if you put 22.44 in, you've got to put in 2.56 kilowatts of power, and they will add up to the 25. I think that's I think we're finished. Is that's what they wanted, wasn't it? See, that's the minimum. If the thing ran perfect, if it ran perfect, that's the minimum. So I'm helping you out here on your homework. That's what I want. Yes.
Can you go over the problem 586E?
586B,
E, the English unit problem.
586E.
Yes.
Yeah, I guess we could, but we better hurry here, Mohammed. Mohammed wants me to do this, so we're going to do it.
Yeah, just do the last part. What is the heat rejection amount is? I'm just confused on that part. You don't have to do the all process.
Uh-huh. Okay.
Just the last part. What is the heat rejection?
Well, let me see here, Mohammed. Let me erase all this. Now, they said it has an efficiency of 45% and produces a net 1,500 megawatts of electricity. Okay. How much coal is used per hour, and what is the heat rejection? Mohammed, I'm gonna have to start from scratch to understand what I'm doing here. Mohammed, you want to draw it clockwise because it's a power cycle,
Yes.
and you want to draw these like so. This is your QH. This won't take long. We can do it. I don't think they give you the TH or the TL. I don't see anything in there about temperature, do you? What we're doing right now is Mohammed needs a little help on part of this 586E. And they did not give you any information whatsoever about temperatures. I don't see anything. However, they did give you this. Now, this is efficiency. And what that is W dot over QH dot. That is 45%. They gave us that. And it produces 15. They did give you this. Look here. They gave you 1,500 megawatts of power. Okay. Hey, we can get, look at here. We got this. In this, we can get the QH dot, Mohammed. Yay, here we go. And that's going to be 1,500 divided by 0.45. I'm getting 3,333 megawatts. And I bet Mohammed got that, didn't you, Mohammed?
Yes, I did.
Yeah, he got that. That's not his problem. Now we're going to answer his question. Coal releases 12,500 BTUs per pound mass when it burns. Now we have to decide what that is. Is that a Q? Is that a Q or a little q or a big Q dot or a little Q dot, Mohammed? Which one of these choices is that? You can tell by the units. Which is it?
It's a little Q.
Say that again, please.
It's a little Q.
It's the little Q. It's not these. This is a little Q. You can tell by the units. Now what they want is m dot. I don't know if you understand, but this is what they're asking for. They want the mass flow rate. Well, now here's how it works. That's actually QH, you know it? It's at the hot temperature. Here's how it works. Big QH is equal to m dot times little QH. And looky here, we know little QH and we know big, hey, Mohammed, we can solve for the m dot, see it? Yeah, that's what we're going to do. Well, here, let's write that down. I need this room here. We got 3333 megawatts is equal to m dot times 12,500 BTUs per pound mass. Uh-oh, we're going to have to convert, Mohammed. Go flip around, start snooping around here. We got to find out BTUs per pound mass. I'll find it here in a little bit. I just have to keep snooping here. Energy, BTUs per pound mass. Well, no, yeah, that would work. Power, we really want power. BTU, okay, I'm getting mixed up here. Watts. We want watts, we want BTUs. We're trying to convert here. And what do they want for the answer, Mohammed? They want the m dot. Okay. We got a problem with the units is what it amounts to. And there's several ways to do it, is the thing about it. Okay, well here, let me show you what I found. I dug around in the back there. And here's what I found. I found 1 kilowatt is equal to 3412.14 BTUs per hour. Okay. So so what would 1 megawatt be? That'd be 1,000 of those, wouldn't it? But probably we want it per second. So do this with me. An hour is equal to, isn't it 3,600 seconds, guys? And so what you'd wind up with would be 3412.14 divided by 3,600. I'm getting 0.9478 something BTUs per second. But we don't have a kilowatt. We're dealing with megawatts, so that's no problem. 1 megawatt is just 1,000 of those. So that would be 947.8 BTUs per second. Mohammed, are you with me to here?
Yes, sir.
Yeah, great. So here's what we're going to do. We're going to multiply this by 947.8. We're going to multiply by 947.8 BTUs per second is equal to 1 megawatt. And see, you can cancel the megawatts and you'll have BTUs per second. And so this will give you pound mass per second. Mohammed, I want you to put this in your calculator and tell me what you get for your mass flow rate.
Professor, I'm hesitating here. I think backwards a lot, but did the decimal point go in the wrong direction for the megawatts when you converted that? I thought the number would have gotten smaller.
A mega is 1,000,000 and a kilo is 1,000, right? So isn't a mega bigger than 1,000?
Right.
So if you have 1 kilowatt, a megawatt would be 1,000 times that. Does that make sense? You don't want to make it smaller. A megawatt's bigger than a kilowatt. A megawatt should be bigger than a kilowatt, right?
Yeah.
I kind of agree with him here, because
Yeah,
if
how can you have
you have
more?
less than 1 kilowatt and end up with almost 1,000 megawatts.
A 1 kilowatt is equal to 0.947.
Oh, I see now. I see now. You're right.
1 megawatt is going to be bigger than that.
It's going to have more BTUs in it than a kilowatt would.
That's right. In fact, 1,000 times more.
That's right. Thank you.
Okay. You are so very welcome. Now, what we're doing right now is we're solving for your MDOT. Okay, well, let's see. Here goes.
I got 9.1 10 raised per 5 pound mass per hour.
Just a minute here. I'm almost there.
Okay.
And let's see, 947.8 times 3333 divided by 12,500. What'd you get for MDOT?
9.1 10 raised per 5 pound mass per hour.
How come I'm getting 252.7? Okay, now just a minute. See, that's BTUs per second. Yeah, and this is pounds mass per second. So that'll be BTUs per second. So I'm getting 252.7 pounds mass per second. It's just an equation. Put it in your calculator. What do you get? Mohammed, take this number times that number and divide by that number and tell me what you get.
Yeah, I got the same. Yeah,
Yeah.
I missed. Yeah, I missed.
There you go. So Mohammed, are you happy now?
Do you know how we can calculate the last part of this problem?
I thought that was the last part of the problem.
No, but when it's saying the heat rejection, what is the heat rejection?
Oh, okay. Well, just a minute. I got lost. What problem are we doing, Mohammed?
586E, that it's the same problem.
Yeah. Just a minute. I got lost. Okay. How much coal is used per hour? Oh, well, we never really answered them. That's the coal per use per second. if you want the coal used per hour, you're going to have to multiply by 3,600 seconds is an hour, and you can get the coal used per hour. Now, the heat rejection, what did they say? It's 45%. I had this a minute ago, and I think I erased it. It's 45% of that. So we take 3,333 times 45%. You get, let's just round it off to 1,500 megawatts. The heat rejection rate, you just subtract these, Mohammed. Subtract that from 3,333, and I'm getting 1,833 megawatts is your heat rejection. See, these have to add up to that.
Okay,
Are
thank
you
so
okay
much.
now?
Yeah, I'm okay. Thank you.
Okay, you are very welcome. Well, I'm going to erase all this, but now I've shown you guys what I want. I want this, well, it's either going to be clockwise or counterclockwise, depending on the cycle. But now we're going to do a Carnot cycle, and this one here that we're going to do, let me see if I can find what I'm going to do here. Kind of got lost here, just a minute. Totally organized. Yeah, I want to do 5104E. Now you're going to do one just like it, and I want you to do what I do on this one. Now this is going to be harder because this is English. But here's your PV diagram. It's air. Find that 5104E with me. Help me find it here. Yeah, there you go. And we got 1,200 Rankine and 600 Rankine. So I'm going to draw those. Here's 1,200 Rankine, 600 Rankine. And here's our Carnot cycle. Remember Carnot cycles? They have an isotherm. They have an isothermal expansion, and then they have an adiabatic expansion. And then they have an isothermal compression. And then they have an adiabatic compression. There's your Carnot cycle. Now we have the temperatures. And it says here, the heat added at the high temperature is 100 BTUs per pound mass. We have a heat transfer here. And this would be a little q. It's a little QH. I can tell by the units. It says here it's 100 BTUs per pound mass. You can tell by the units that that's a little q. The lowest pressure in the cycle is 10 psi. Well, that would be here at 3. At state 3, we have 10 psi. Okay. And here's what we're going to do. And I want you to do this on your homework problem. But your homework problem, I think, is number 59, is it? Let me see. Is it 59? No, it's not. Your homework problem.
49.
Say it again.
49.
39
49.
or 49? I can't hear good. Yeah, right. You're gonna do 49. Now I want you to do the same doggone thing that I'm gonna do. We're gonna make a table of values here. We're gonna make a table of values. And this is gonna be process. We're gonna go from 1 to 2. Oops. This is gonna go from 2 to 3. What's 2 to 3? Is that that's the adiabat, isn't it? And then we're going to go from 3 to 4. Then we're going to go from 4 back to 1 because we have a cycle. We're going to fill in each one of these boxes. Now we already know some of this stuff. Now what I'm going to put in here is the initial amounts. Put a little I there. Those are the initial properties when you're starting your process. See, when you go from 1 to 2, at state 1, the temperature is 1200 Rankine. That's the initial temperature. Now, when you go from 2 to 3, the initial temperature is still 1200 Rankine, isn't it? Now, when you go from 3 to 4, the initial temperature is 600 Rankine. So you can put Rankine in here. And then when you go from 4 to 1, the initial temperature is 600 Rankine. Now, they were very nice, and they gave us the lowest pressure. That's the pressure at 3, and it's 10 PSI. You put a little PSI right there. Now, look at here. We know P3 and T3. Look at here. P3 V3 equals RT3. We know P3, we know R, and we know T3. We can solve, it's air, we're dealing with air, we treat it like an ideal gas, and we can solve for the specific volume here at state 3. Now, I'm going to shut up for a minute, and I want to see if you can do that. Okay? Fine. What we're doing right now, if you just woke up from a daydream, we're trying to find specific volume at state 3. We're going to put it in this table of this property table. Okay, on your mark, get set, go. I'm going to do it. You do it. We'll see if we can agree. Well, I got an answer. Let me call on somebody here and see if anybody's got that answer for me. How about my friend, let's see here. I have trouble pushing the right buttons on this thing. William, unmute and say hello, please. Earth calling William. Come in, William. Uh-oh, coffee break. Tyler, you're here with me. You're not going to let me down. Unmute and say hi, Tyler.
Hello.
Tyler, did you figure out little V3 yet?
I got 3,260.4.
Nah, something bad happened, Tyler. Here, let me write it out for you. Okay, we know P3 is 10 PSI. You know what that is? That's a pound force per square inch. That's what a PSI is. And then V3 is what we're trying to find. Now R, if you look it up, we're in Inglés, senor. It's 5334 foot-pounds force, pound mass Rankine. And T3 is 1200 Rankine. Now to get this to work, Tyler, you got to do this dirty little trick right here, or else it doesn't work. There's 144 square inches in a square foot. See, this is going to be cubic feet per pound mass. So you'll wind up with a foot pound. The inches squares cancel. You'll wind up over here with foot pounds per pound mass. And guess what you have over here? Foot pounds per pound mass. The Rankines cancel. Now, Tyler, do it again and tell me what the V3 is.
Is it 463.02?
Nope, do it again. Take that number, multiply by that number, and then divide by that number, and then divide by that number, and tell me again. Try it again. I know you can do this. I have faith in you.
Okay, I'm getting 44.45.
That's not what I'm getting. Oh, now wait a minute, Tyler, that's what I got. Something bad happened. I must be telling you something wrong. Tyler's doing it right, but that's not the right answer.
Should we be using 600?
Oh,
1200?
Here's my problem. Tyler, it's not your fault. I'm plugging in the wrong temperature. Auga, the temperature at state 3 is not 1200, it's 600. So one last time, Tyler, that wasn't your fault. Put in the 600 and tell me what you get. We're going to get this right between us. I gave you the wrong temperature.
All right, I'm getting 22.225.
Yay, that's what I got. 22.225. We're working now. And you know what that is? That's cubic feet per pound mass. We're doing great. Now, here, let me get these delta U's for you. Those are pretty easy. There's a little room up here. See, delta U is equal to C sub V delta T for ideal gases. Okay, great. Well, you have to go look up C sub V. Well, in the back, I can show you where it is, but it's 0.171 BTUs per pound mass per Rankine. Now to go from state 1 to state 2, it's an isotherm. There is no change in temperature. So this one here will be 0, and so will 3 to 4 because it's an isotherm. Delta T is 0 for isotherms. Temperature doesn't change. But now going from 2 to 3, the temperature went down from 1200 to 600. I want you to plug in the delta T here and get me this delta U. We're not picking on Tyler anymore. He's paid his dues. I want somebody else to do it. Y'all do it. Little Southern talk. Find out delta U. I'm going to do it, and I want you to do it. And we'll see if we get the same thing. We're right now, we're trying to find the change in specific internal energy going from state 2 to state 3. Going from 2 to 3. And I think I have the answer. Let me ask one of my excellent students here. Let's pick on Taylor. Taylor, unmute and say hello, please.
Hello, please.
Okay. Taylor, did you get this change in specific internal energy going from 2 to 3?
I came up with 102.6.
Yeah, now is that plus or minus, Taylor?
That's going to be a negative.
There you go. He got it right. It's negative 102.6. Good going, Taylor. Now, as long as I got Taylor on the line here, let's do the delta U from 4 to 1. Now, that's going to be the 171 business again. Do I need to show anybody where I got that 171 out? Just say the word and I'll show you in the back, or you can find it yourself. Taylor, go from 4 to 1 and give me the change in specific internal energy from 4 to 1.
Now, wouldn't that just be a positive 102.6?
Yeah, good going. It's just a positive 102.6. That was easy. So we're doing great. Now, you know what? They gave us this. You see that 100 BTUs per pound mass? By the way, these are BTUs per pound mass, aren't they? They're BTUs per pound mass. But see, they gave us this from 1 to 2. It's 100, but now here's the question: is it plus or is it minus 100 BTUs per pound mass? Now, I'm going to ask one of my excellent students here. It's BTUs per pound mass. They gave us that. But is it a plus or a minus? Nicholas, unmute and say hello, Nicholas.
Hello.
Hey. Nicholas is in 3 of my classes, aren't you, Nicholas?
No, sir. Just one.
Oh, it's a different Nicholas. Yeah, I do have a Nicholas in 3 of my classes, but that's Nicholas. Oh, I forget his last name, but never mind. You're in this class, Nicholas, and what I need to know is this heat transfer 100 BTUs per pound mass? Nicholas, is that plus or minus?
Is it negative?
Don't go to the casino. You had a
Oh,
50,
no.
50. You had a 50-50 chance. Don't go to the casino. It's positive. See, heat transfer in is positive. Heat transfer out is negative. Now, when you jump in the swimming pool and you get out and the wind's blowing, ooh, you're cold. The wind is blowing on you and you're wet. That's a heat transfer out. That's negative. You get cold. So now you know. Well, we're doing great here. Now, there's two of these little Q's that are zeros. Now, those are the adiabats. Do you remember Carnot? This is a Carnot cycle. Carnot cycle. These are adiabats. They don't have any heat transfer. So a couple of these Q's are zeros. Which ones are they? Let me ask one of my excellent students here. Braxton, I think maybe I picked on you already. Was that in the last class that I picked on you, Braxton?
Yeah, I think it was last class.
Well, this is a different class. This
Yeah.
is a different. Yeah, it's a brand new world now, Braxton. Now, what I need to know is which Q's here do I put zeros in?
The 2 to 3 and 4 to 1.
You got it. Good going. See, those are adiabats. Adiabats don't have any heat transfer. Now we can get this. Let me show you how to get that. But I need some room here. You don't need any of this jazz here. Let's just get rid of it. I've got this little corner that I can work in here. See, the Carnot cycle is a perfect, ideal, reversible cycle. There's no friction. There's no irreversibilities at all. And the actual efficiency of a Carnot cycle is equal to the maximum possible theoretical value of the efficiency. So we can write those equations. See, the actual efficiency in this case would be little w over QH. Now the theoretical efficiency would be TH minus TL over TH. Now we know this, they gave it to us, and we know all of these, so we can figure the work per mass output of this Carnot cycle. I'm going to shut up and I want you to find the work per mass of the Carnot cycle. I wonder if that's enough time. Let me go to one of my wonderful students. Brian, unmute and say hello, Brian.
Hello.
Brian, did you figure out what that work per mass is on this Carnot cycle?
I did not.
I like honesty. That's a good, honest answer. Let me try Bryce. Bryce, unmute and say hello.
Hello.
Bryce, have you figured out this work per mass on this Carnot cycle?
Below the W, is that a QH or does it say?
Yeah, that's a QH.
Um,
That's supposed to say QH. See, we know what
Okay.
QH is.
say 50.
Yeah, good going. W is 50. Hey, look here. W is 50, but now you got to understand something. That's the network. That's the network. It might be helpful for us to draw the cycle. You know, it's clockwise. Let's draw this clockwise cycle. Here comes your little QH. It's your high temperature. We just did one of those. Mohammed had me do one. And he seemed to be okay at the end. You got to understand, this is the network. We're going to have 4 works here, but the network is the grand algebraic total of all of them. But I know what this is. It's 250. And I know what the efficiency is, because this is 1200 minus 600 over 1200. You know what? That's 0.5, isn't it? And so if this here is 100, like my student just told me, this is going to be 50. So what's
200.
it sure looks like, no, wait a minute, this is wrong. Somebody could have
Right.
gotten a thank you point. That's not 250, that's 100. I don't know why I wrote that. It's 100. But you were correct. Only I had the wrong number. This is going to be 50. Only when you write it in here, this is going to be a negative. Here, let me draw it for you. This is your QL. It's a negative 50. Now, let's add these up. If you add the total on here, well, here first, let's get the little w's first. And then you'll see that the total will be 50. Okay, now, here's how you get those little w's. Let me make some room here. I don't have much room to operate here, but there's enough. It's sufficient. We're going to use the first law of thermodynamics for closed system. This is a piston cylinder deal. Piston cylinder, and we're going to use this equation here. Now on state 1 to 2, going from 1 to 2, this is 0. This is 100. So what's the work per mass? What's the little w going from 1 to 2? What do you think?
100.
It's 100. It's 100 BTUs per pound mass. Good going. Now we can do the same thing here. The change in specific internal energy going from 2 to 3 will equal, well, in this case, it's 0. There is no Q. That's an adiabat minus the work per mass from 2 to 3. So what's the work per mass going from 2 to 3? What do I put right here?
$102.6.
Yes, and it's a positive 102.6, isn't it? Now, who was that just spoke?
Taylor.
Taylor. Thank you, Taylor. Good going. Does that compute? Let's write it out. If this is minus 102.6, and that's 0, and there's a negative because of the first law, and this is a positive 102.6, does that compute? Well, boy, Jove, it does. So we're doing great. I'm going to shut up for 60 seconds and I want you to get these two. Go ahead and get those two. Hey, we're doing great. Look, we're filling this whole thing in. I want you students to find the work per mass for processes 3 to 4 and 4 to 1. Go for it. Well, let's see if somebody can help us out here. How about my friend Bryce? Hey, Bryce, did you get the work per mass that goes in these boxes here, Bryce?
Certainly did.
What'd you get?
The answers are -50 and -102.6.
You're absolutely right.
Thank you.
Good going, Bryce. Does anybody need me to write that out?
No.
I guess you're okay. Hey, look at here, we're doing great. All we got is 6 boxes to fill in, and we'll know pretty much everything there is to know about this Carnot cycle. Now, when you do your homework, you're going to do 549. I believe that's the number. 549. Yeah, I think that's right. I want you to make me a table just like this. Only it's in English. No, it's in metric. So you won't have PSI, you'll have kilopascals, I guess, kilopascals. You won't have cubic feet per pound mass. You'll have cubic meters per kilogram. You won't have Rankine, you'll have Kelvin. You won't have BTUs per pound mass, you'll have kilojoules per kilogram. Kilojoules per kilogram, kilojoules per kilogram. But I want you to make the same chart here, the same table of values, and I want you to fill in all of them. Fill it all in. That's your homework. 549. I'm showing you how to do it, and I'm doing an English problem, which is ugly. English is just hard, but we can do it. Okay, well, we've made a lot of progress. Let me make some room here. You're going to do that. That's your homework. That's your homework.
Do you want us to fill out the pressure volumes as well?
I want you to fill out all the pressures for each process, all the specific volumes for each process. I want you to make a chart just like this
Gotcha.
and fill it out. Fill it out. Just like I'm doing it on this problem 5104E, but you're going to do it on problem 549. Now you're lucky because that's metric, which is easier. This is ugly. Well, let's finish it off here. We got time. I think we got 20 minutes to finish this. We'll make it. Okay, I've got an idea here. I want you to look at process from 1 to 2. We have an equation for ideal gas isotherms. I don't know if you remember it, but it goes like this. Yeah, that's a nice equation, but it isn't gonna do us any good. Because we don't know P1 and we don't know V1. And we don't know V2 and we don't know V1. Never mind, that isn't gonna help any. It was just a thought. Just a thought. But now, wait a minute. Auga, I just had a thought. We have another isotherm that goes from 3 to 4, don't we? Do you guys remember this equation? We studied it. In fact, I derived it. I derived it from scratch a long time ago. Might have been in September. This is October. But hey, look at here. We know what the work per mass is from 3 to 4. Hey, it's, we got that. It's negative 50. Yeah. Do we know P3 and V3? Yeah, looky here. We know that. We know those. Yeah, we know those. Do we know V3? Yeah. Hey, looky here. Here's an equation with only one unknown, V4. We can you see that we can get V4 this way? It's possible. Es posible. All right, so let's do it. Here goes. I'm going to write the, that's your homework. I don't need that there. You can look it up on your Blackboard. We know this is thermal class. We know this is 2020. We know we're doing a Carnot cycle. You got lots of room up here. Okay, the work going from 3 to 4 is minus 50 BTUs per pound mass equals P3V3. Well, what's P3? That's the 10. It's the 10 pounds force per square inch, right? P3. What's V3? 22.225 pound cubic feet per pound mass. Okay. We're going to have to doctor that up. I can see that right now. And then we're going to have to multiply. We're going to have to put some stuff in here. Then we're going to have to go natural log V4 over V3. Now V3 happens to be 22.225. But we need a conversion in here. Now here's the conversion. We need foot pounds. So I'm thinking we need 144 inches squared per square foot. That'll get rid of 2 of those cubic feet and give us foot pounds. And then we need a BTU is 778.17 foot pounds of force. And you see, that gets rid of the pounds of force, and gives us BTUs. That's what we want. We want BTUs. We got BTUs per pound mass. We got rid of the square inches. And we got rid of the foot pounds. Yeah. Hey guys, that's it. But you see how important units are. All right, get your calculators. Plug all this stuff in and solve for V4 for me. I'll shut up for a minute and I want to see if you can get that. See, that's going to go right here. Go for it. Let's see if you can do that. Okay, I don't know if you got there yet, but you should. How about my friend Brian? Brian, have I picked on you today yet?
Only a little bit.
A little bit. Well, let me pick on somebody else.
No, it's fine. It's fine.
How about Alex? Alex, have I picked on you today?
In your other
So-
class, I goofed up my equation. I left out that 22.2, so I'm having to redo mine.
Oh, that's okay. Put it back in there. Let's go with my friend Braxton. I'll pick on you again, whether I have or not. Braxton, did you put all these numbers in and solve for V4 yet?
Still doing it.
Yeah, take your time. Take your time. I can write it out if you guys need me to. How about my friend, hey, William. William, how about it? Do you have that little V4 figured out yet?
I do not.
Well, get your calculator and put in minus 50 and then divide by 10, divide by 22 or something, divide by 144, multiply by 778. Maybe we should do these in stages. Here, let me do that. I'm going to do what I just said. I'm going to take negative 50. I'm going to divide by 10. I'm going to divide by 22.225. I'm going to divide by 144, and I'm going to multiply by 778.17. And here's what I've got. I've got minus 1.2157 equals the natural log of V4 over 22.225. And what you do now, guys, is you punch that little e to the x button. Punch that little e to the x button, and here's what you'll have. You will have 0.29649 equals V4 over 22.225. And then you can get your V4. Multiply. And here's what you'll get for V4. Well, let me ask you, what did you get? How about my friend Nathan? Unmute and say hi, Nathan.
Hi,
What'd you get for your V4?
one sec.
We've got our equation here. I know you guys can do this. It's just algebra and a little dash of calculus.
All
I
right,
know
is
you
it
can-
is it 6.5?
Yes, it is. It's V4 is 6.5. I guess you could round it off to 90. How's that? That's pretty good, isn't it? Did anybody else get that? Say uh-huh.
Uh-huh.
Yeah, I need another. Yeah, there you go. Hey, we're making progress. Oh, gee, we only have 8 more minutes. Oh, no. But looky here. We have the V and the T. We can get the P from the ideal gas law. Here, let me write that. I hate to erase all that good stuff. I hope you got it. But you guys take notes. everything I write down on this board, you're writing down in your notes to study later. And if you forgot to do it, you can watch the YouTube. If my daughter can post those on YouTube, she's a busy girl, but she will. She's pretty good about it. But now look here. P4V4 is equal to RT4. Now we did that before. We can do it again, can't we? So it's P4 6.590 cubic feet per pound mass equals 5334 foot-pound force per pound mass Rankine times 600 Rankine. Hey, I got the right temperature this time. I didn't put in 1200 and goof up like I did last time. But now there's a dirty little secret here, guys. We're in English, senor. You got to go 144 inches squared per square foot, or else you won't get the right answer. But I think that will. All right, go ahead. Find P4 for me. I'll shut up and I want you to find P4. I wonder if anybody got 33.73 PSI. If you did, say uh-huh.
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 That's what I like to hear. Well, let's put it in here. 33.73. We're learning how to do this. We only have 4 more boxes, but we only have 5 more minutes. It's going to be tight, but we can do it. I need this room though. I'm going to have to, you don't need that. You know the ideal gas law. You can do that without me. Now to get these 4, we're going to have to work with the adiabats. Now later I'll show you an easier way than this. But in chapter 5, there's a couple of equations on page 160 and page 161 that deal with adiabats. Now one of them goes like this. You'll see this equation on page 160. I hope you can read my writing. That's supposed to say natural log right there. Then there's another equation on 161 that goes like this. Well, it's basically the same equation. We're dealing here with the adiabats. See, one adiabat goes from 2 to 3. It goes from a high temperature to a low temperature. It goes from 1200 to 600. And it ends up at specific volume at state 3. It started at state 2. It goes from 2 to 3. It's the adiabat. And I'll show you later where in the heck this equation came from. But on page 161, the other adiabat goes from 4 to 1. Well, that goes from the low temperature to the high temperature. It goes from 600 to 1200. And this goes, the final specific volume is at state 1, and the initial on the process from 4 to 1 is V4. So here, let me, I've got 3 minutes left. I got time to do this first one for you from going from 2 to 3. See what this is from 2 to 3, going from state 2 to state 3. Okay. Now you can pull that C sub V out, and it's just 0.171 BTUs per pound mass Rankine. We've had it on the board a couple of times already. And see, when you integrate that, what you'll get is a natural log of the temperature. And if you go from high to low, the final is the 600 and the initial is the 1200. Now R is 5334. Uh-oh, I'm going to run out of room. I can see it happening. Pound mass per Rankine. Natural log, let's scoot it over here. Natural log of V3. Can you read my writing? Natural log of V3 over V2. But see, we got to have the same units. Now these are BTUs per pound mass. We can do that. See, a BTU is 778.17 foot-pounds of force. You could look it up in the back. But now I think you have BTUs per pound mass Rankine. And here you have BTUs per pound mass Rankine. So it'll work. All we got to do is plug and chug in our calculators, and we can get we can get V2, because see, we know V3. V3 is 22.225. So, oh gee, I'm out of time, but I can tell you what this is. You can do it on your own to feel good about it. And what you get for V2, what you'll get for V2 is, if you plug in all these numbers, you'll get 2. No, that's not right. You'll get 3.929 cubic feet per pound mass is what you'll get. And now you can get P2, because P2 V2 is equal to RT2. We've done that several times before. Now to get this one here, use this other equation that I had to erase on page 161, and you can get these last two. Well, I've shown you how to do it, and now you're going to do 549 for me, and you're going to make a chart just like this, and you're going to fill it in. Well, it's sad, but our time together has come to an end. Did you have any other last questions or comments? Well, okay, I'm going to push this red button here. I will see you guys, I don't know, when do we see you? Next Tuesday at 11, maybe? That'd be good. See you then. Enjoy. Bye-bye, students.
Have a good day.
Have a good day,
I
Mr.
will.
Griffin.
Thank you. You too. Be careful.